recorder or not, but have so many things open now, it usually gets buried somewhere and I can't see when it's recording. That's why I like to do it while I can still see it. So let me go on and start the screen share with 7. Now why in the world my email is here, I don't know. And I can't tell what that one is. I'm pretty sure I don't want that one. I can't tell what this one is. This is nuts. There's 7.3. Now we're not in 7.3 yet, but we will be. The last example in 7.2 is not on the PowerPoint. So anyway, so let me come down here and move this. You can't see it, I hope, but it's a toolbar that's right in the middle of the lower part of the screen. So I'm trying to get it out of the way so I can see the PowerPoint. And I'll go on and get this slideshow set up, even though we're not going to start it yet, from the current slide. And we'll go on and get the whiteboard set up, because that's where we'll be using. Okay, still don't see. Yeah, there it is. There's the other PowerPoint. Okay, so let's start with the whiteboard. And let me get this toolbar out of the way, because that's right where I'm needing to write. And also scoot the whiteboard over as much as I can to get maximum amount of white so I can write as much as possible. Okay, and I think last time I had the new whatever they call it, Wacom board, so that makes writing on the white pad easier. Not completely easy yet, and I'm still in the habit of using my finger, so I'll sometimes get crossed up, and I'll also try to move things around on the with my finger on the Wacom, which doesn't work. I have to move it and use the keypad. Okay, now I don't know what Alt. I must have hit that by mistake. Okay, I'm having to set this on the keyboard so I can use it better, and it sometimes will press a key that I don't want it to press. All right, any questions, issues, concerns before we get started today? All right, we're in the very last example, and we're in Chapter 7, Applications of Integration. 7.2 is volume the disk method, and this is the last example on page 460 in that section. So let's hit this last example. If there are no questions, no issues, no concerns, let's get started. Okay. Prove that the volume of a pyramid with a square base is this. Okay. And let me get the, here is the volume of a pyramid with a square base is 1/3 the height times the base. Excuse me. The height times the base. And the capital B means the area of the base. Okay. Now, I don't draw pyramids very well. I don't draw much of anything very well. And if you got your books, you can see it. If you don't, there is what it looks like. There is the pyramid, square base and some height H. Okay. Now, as you may have seen in that, it was hard to hold. There was a representative slice of that pyramid. Okay, going up. Let's see if I can get it. You see that slice there? That is a square going from the base at 0 up to the height of H. So it looks like we're going to be doing D I can't tell, but it should be a dy, I assume, or I think a dy, okay, as we're going up from 0 to h, okay? And every one of those cross-sectional shapes is a square. So we know what the area of a square is, all right? Now, what they're going to do here, every one of those representative squares that you can see in that has, let's see, kind of hate to do this again, but I will do it again so you can see what I'm talking about, okay? I don't know if you can see that. The base of that pyramid they're calling little b, the dimension is the word I was trying to say. The dimension of that base is the base is little b, making the area of that base capital B, okay, little b times little b, and the length of any square segment as you go up, that's going to be what they call b prime, okay? So the next thing they're going to do is break that square that you see there that they're calling a of y, excuse me, and they're going to just take a triangular cross section of that. Now you notice that's half of b prime is that triangular cross section, okay? And the height is h, so that's a cross section in the xy plane of that the image we just had there. And I'm tired of holding the book, okay? So with that in mind, okay, I'll try to draw sorta the that second figure because we're going to be working off of that one, okay? So what I'm going to do here is draw with some straight lines here, and these are not going to be pretty, but they're better than my drawing, okay? And I will try to draw the y-axis here, which I'll do something like that. I don't know if I'm at all, not quite vertical, but close. Okay, the x-axis, I don't need that much on that side, mostly on this side. Okay, not very horizontal either. Okay, and then I will do, where is my pen? There it is. Okay, I will do a line from here to there. Now, not a very good drawing either, but let me also get in there. Okay, now I don't know how to keep it from wanting to move it. Okay, maybe that worked. Okay, now I'll show that yellow portion there to there. All right. Oops. Okay. It won't pick up and move it. Okay, there we go. I can't get it to move. It's supposed to move. Well, if you can live with that, let's see if I can get this end to move. I don't think I will be able to. No, it won't. Okay. I'm going to quit messing with it. Now let's go back to my drawing. And I'm sorry about that. I can't get it to straighten itself up. Okay. Now let's get what we have. Based on what we had before, this dimension here is 1/2 b prime, where b prime is the edge of that square wafer you had there. Now they don't list this in the book. I wish they would. This is your dy. Yuck. I hate when it does that. Okay. Okay. Let me Try again. Why it won't write Y? Okay, there it is. I have to write fast or it messes up. Now I just heard a sound, but we still got 7 students. Let me make sure. 1, 2, 3, 4, 5, 6, 7. Now I've got 8 students. We must have lost somebody, or marked someone that. Okay. So watch. It looks like someone may be trying to get back in, because it says down here we have 8 present participants. I'm one of them. That would be 7 students, and I've got in my book that we have 8 present today. Ah, here we go. Well, but he wasn't here before. Oops. Let me get Jesus here. Okay, he's on the blue line. Okay, I got Jesus here. Now, okay, we're trying to verify, Jesus, if you just got here. We're on Chapter 7, Application of Integration, 7.2, volume, the disk method. We're on page 460, the last page in this section of examples, example 7, the last example in this section, and we're trying to verify that this is the equation for a pyramid with a square base. Actually, it's a formula for any pyramid, but we're doing one with a square base, okay, where capital B is the area of that base. Okay, now here's our drawing. This is a cross section of taken in the XY plane, and maybe I should put that down. So this is the x-axis, and this up here is the y-axis. Okay, and this is the cross section here of that, and there's a slice in that pyramid, and that top line is supposed to be horizontal, but I couldn't get it to go horizontal. I tried and tried, and it just fiddled with me. So anyway, that's supposed to be a slice. Now this is a cross section. The length of that base, that little base up there, of that slice, the square slice, is B prime. We're just doing half of that in this section, so that's 1/2 B prime. Okay. Now, other things to note here is this height here. If I can get it to go there, this is the height of the pyramid. I can't draw my brace very well. That is your H. Okay. So we're going to be integrating y's, because you have your dy here, from 0 to h. Okay, just to give you an idea. Now, the dimension down here is your base, and that's b over 2. Okay, 1/2 b, the way the book writes it. Okay, now the other dimension, now I put my h probably on the wrong side, that we need to do is this one here. Okay, now this is your y, your variable y, not the y-axis, variable y. So this would be h minus y. Okay, I still can't get the minus sound to draw, and this irritates me why it does this kind of weird thing. But okay, that's a pretty ugly minus sign, but there it is, h minus y. Okay, now, all right, what the issue is that we're trying to do is find the area of this slice. Okay, now this slice, I'm going to pretend, and I'm not doing, in fact, let me go back to my draw screen here. It was bad the first time. I'm sure it's going to be bad this time too. I can't get the pen to go up there. There we go, finally. I don't know why it's being, there we go. Okay, now I'm going to select, well, let's see. Maybe I should use a select here. Let me try that. Okay, I'm going to select this line here. Okay. Now with this, I'm going to go, again, it's not cooperating. Okay, I can't do what I was trying to. Now it moved when I didn't want it to. Ah, there we go. Now, why it's going in the opposite direction of where I'm trying to get it to go, I do not know. And it stopped there. Okay, so let's see if I can select another one. Select that one. And now maybe I can get it to go where I want it to go. Okay, now what I'm trying to show here is that is the whole slice that we want. Okay, that length is B prime. Okay, but we're dealing with just this portion here. What we need to get is, because we're doing, let me get rid of this and get back to our draw mode. Okay, what we're doing, we're needing to get, wait, here's Kira. Oops, I keep wanting to use my finger and I can't. Was Kira here before? I think she was, wasn't she? Yes, so that's who we lost and she came back. Okay, but is somebody else here? Can anyone see who that was who just came in? Now something fell and I don't know what it was. I heard it hit. Okay, Kira, right. But it looked like I just let somebody else in the, oh, it was Daniel Thaxton. That's who it was. Oh, it was my pen. Okay, I think I found my pen. Okay. Sorry, everything's falling apart here. Okay, Daniel Thaxton came in. They black out the names so I can't see who's coming in the course, and it's a really stupid feature. Oh, here's Jemanuel coming in too. That time it faded out enough for me to see Jemanuel. Okay, so let me get Jemanuel here. There he is. Okay. All right. Now, what we're trying to do, going back to this, is find the area of this length here. Okay, and we want it in terms of, okay, here's somebody else coming in and I can't tell who it is. Can anyone see this? I couldn't see it. It blocked me out. It may have been Jemanuel again. I don't know. Jemanuel, did you make it in the first time? We're up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, I think that must have been Jemanuel coming in. Okay, so what we're trying to do, if I can get back to this, is find the area of this piece right here. Okay, we know its dimension here is 1/2 B prime. Okay, but we don't want B prime. We want that in terms of Y because we're going to be integrating in terms of Y. But we do know this. Okay, wait a minute before I say we know it. We know a ratio. Okay, here's the ratio we know. We know the ratio of this half base to this height. Okay, so let's write that down. B over 2 divided by H. Okay, now up here we also know that that's the same ratio as B prime over 2 to H minus Y. Okay, so that's equal to B prime over 2 divided by H minus Y. That's a pretty ugly Y. All right, so what we're trying to do is get the B prime here in terms of the Y down here, because B we know, H we know, We just don't know b prime, but we don't want it in terms of b prime, we want it in terms of y. So that creates a proportion here that we can multiply through. And by the way, we can multiply both denominators by 2 and have absolutely no loss of generality. So let's just get rid of those 2's there, okay? Now, so what we have is that the b prime times h is equal to b times h minus y. And then we were dividing both sides by the h to get b prime in terms of y, where b and h are both constants. Well, I don't know if it's helpful any, but we could write that as b minus by over h. Okay? B's, let's see, I think I need an h here too. B over h. That's a constant. Okay? I think I did that wrong. No. I did do it wrong. The h is not there. Okay? This is bh over h, which is b minus by over h. I had it right the first time. This is a constant, b. So that's not going to be anything really to worry too much about. But that's what your b prime is. And we're going to do half of that. So b prime, okay. So that gives us this dimension right here. Okay, or almost. Half of that is that dimension right there. Okay, now the thickness of that is dy, of course. Okay, the area of that would be b prime times 1/2 b prime. That would be the area of this thing, and that's what we're taking from bottom to top, integrating it with respect to that. So let's do half of this. If I could get the pen to right. Okay. Half of that will then make this now at over 2 and this over 2h. That's our length of that. Our width is what we just had. So basically I'm going to go back and rewrite it this way. The length times the width would be 1/2 of b minus, oh that's ugly, by over h squared. Okay. That would be 1/2. Yeah, this is it's hard to show it in 2-dimension what we want in 3-dimension. Here is the length, okay, 1/2 by, which is what I had written. Yeah, my pen goes away. Had written there, and then the length of that, if we had imagined, the full length of it, that would just be b prime. So you have the 1/2 of that times b prime. Okay. Now that gives you the slice that's going up from 0 to y. Okay. 0 to h, I'm sorry. The y is going from 0 to h. Okay. Now, we're going to double this because that's just half of that pyramid. The other half's on the other side, so that takes care of the 1/2. Okay. So now I believe we've got everything we need to do our integration. The volume is going to be the integral of b minus by over h squared dy. Okay, let's go back and make sure we've got this down. Okay, the b minus by over h is the length That's the b prime that we had here. And b prime squared is the area of that plate that's going up from b is equal to 0. I mean, y is equal to 0 to y is equal to h. So we're integrating this, if I can get my pen to come back, from 0 to h. Okay, and let's see what we get. Well, of course, let's go on and multiply that out. Okay, did someone just come in? I'm focusing so much on what I'm writing. Okay, let's square that, and that would be b squared minus 2b squared y over h plus b squared y squared over h squared. And that's what we're integrating with respect to y. I'm sorry, all my writing seems to go uphill here. It must be something to do with being left-handed and trying not to be hitting buttons I shouldn't be hitting. All right, so let's see if we can integrate. Are we anywhere close to what they have here? It really doesn't look like it, does it? I think it will come out okay, but let's give a shot and see. Okay, so that's what we're integrating. Let's do the integration. This is going to be a b squared, it's supposed to be a 2, y, not h, b squared y minus, and this is going to give us a y squared over 2, so that's going to be a b squared y squared over h, okay, plus, and this will be a b squared y cubed. Okay, I don't know what made that noise happen. Is someone trying to get in? I can't tell that they are. Let me come down here and see if I can find. No, it doesn't look like anyone's trying to get in. We should have 11 people here. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, all that seems to be okay. So I don't know what makes the little noises here. Oh, here's somebody trying to get in. Now I can't see who it is. Can anyone see that? It starts with a J. I couldn't tell. Could y'all tell who that was? Who is a J that's not been? Who is it? I can't hear. You didn't see who it was? Okay. Let me see. We already have. Okay, did someone just come in? I don't know what these beeps mean. Okay. We already had Jonathan here. We already had, oh, Joy. Was it Joy Robinson? Did you just come in? Let me see. Let me go back here and check and see who just came in. Jalen, that's who came in. All right, welcome, Jalen. All right, that's who it was. Okay, now we're up to 13 attendees. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Whoops, yeah, I'm the 13th. Sorry. Okay. Now, let me go back. I keep trying to activate things with my finger on my pad, and I can't do it. All right, we were doing this integration. We're doing, by the way, those who have just recently come in, we're doing example 7, the last example in section 7.2, which is the disk method of chapter 7, applications for integration. Volume, the disk method. Okay, and we're right at the end kind of doing this, and this was over h squared, 3h squared. Okay, the 3 coming from the integration there. And we're evaluating this from 0 to h. Okay, those are the limits. All right, so you put it, oh, yuck. That's not in there. Just pretend it's not there. When you put an h in for the y here, that gives you b cubed. Okay, if I can get the pen to be where I want it to be. The first term is a b cubed. The second term, plug an h in for the y and you get h squared over h would just be h times b squared. So that would be, okay, I'm sorry, I misstated that. Sorry. Crossing up my b's and my h's. Sorry. Let me go up here to my eraser. Okay, and let's start over here and get this line out of there. Okay, let's try that again. All right, I'm sorry. You put an h in for the y and you get b squared h. I'm surprised no one stopped me on that. B squared times h. Okay, minus, when you put a h in for the y squared, you get h squared over h, which is another h. That's a minus b squared over h. Those add to 0. And then your last one is a plus, and you put an h in for y, and you get h cubed over h squared. Well, that's an h, but you have a b squared on top, so you have a 1/3. That's a 3. Okay, 1/3 b squared times h. Well, guess what? B squared is your capital B. Okay, so that is indeed the same as, if I can get my pen to come back, that's the same as 1/3 h, I would put them in different order, times capital B, because capital B is the area B squared. Okay, we've just proven that. What a pain in the neck it was to do it. Hardly a number in sight here, but we did show that's indeed the volume of a square pyramid. Pyramid with a square base. Doesn't matter what size the base is, as long as it's squared, b times b, little b times little b to give you capital B. And the height, no matter how tall. They don't have to be anywhere related to each other. That's the area, a volume. All right. With that done, let's look at the homework exercises. Do any of the either 5 or 7, this is on page 461 and following, either 5 or 7, they're both at Calc Chat, 5's at Calc View. Either 9 or 11, they're both at Calc Chat, 9's at Calc View. Either 13 or 15, they're both at Calc Chat, 13's at Calc View. Either 17 or 19, they're both at Calc Chat, 17's at Calc View. Either 21 or 23, they're both at Calc Chat, 23's at Calc View. Any of the odds 25 to 31, they're all at Calc Chat. 33 or 35, they're both at Calc Chat. 37 or 39, both at Calc Chat. 37's at Calc View. Any of the odds 41 to 47, they're all at Calc Chat. 49 or 51, they're both at Calc Chat. Now they indicate those you might need technology, a graphing utility. If you can do it without it, fantastic. If not, and you don't have one, don't sweat it. You won't have one like that on your test, I don't think. 53 is exploring concepts. You can do that if you choose. That should be at Calc Chat. 55 should be at Calc Chat. 57 should be at Calc Chat. And then some practical application problems. Any of the odds 59 through 67 should be at Calc Chat. Now 65, again, they indicate you might need a graphing utility. Actually, I probably should have included 69 in that grouping as well. Okay, any of the odds 59 through 69. 65 may need a graphing utility, and 69B may need a graphing utility. Okay, then you can think about doing number 71. It should be at Calc Chat. Now, 73 was not mentioned in the book, but it is a theory, Cavalier's theorem. It's 72, you don't have to do it, but it's a potential paper topic. Who in the world was Cavalieri? Okay, sounds pretty Italian to me. How did he come up with this theorem? What's a practical application of the theorem? Lots of different things you could do with that. So if you haven't chosen a paper topic yet, hint, hint, get going on your papers. Okay, so I think 71 was to think about it. You can do either 73 or 75. Now they're getting progressively more complicated. 73 is not too bad. 75 could be a pain. Okay, so I'll let you decide what you're going to do on that one. 77, volume of a wedge. I'll let you decide whether you want to tackle that one or not. All right, any questions on 7.2? That was calculating volumes using the disk method. All right, where we're going now is to 7.3, which, if I can quit rubbing with my finger, get my pen that's activated, and let's go to a new share here. Oh no, it's not, yeah, it is a new share. It's, I believe it was, oh, 7.3, yeah, that's it right there. Okay, well, there we go. All right, and we'll go from the current slide. And again, it's making some beeping noise. I'm assuming that may be because my Wacom board is resting on a key and must be doing something to the key and making it beep. Okay. All right. So let's move on. Chapter 7, so application of integration. 7.3 is calculating volumes using the shell method. Okay. Now what we're going to do, the objectives here are to find the volume of a solid of revolution using the shell method as opposed to the disk method. We'll compare the uses of the disk method with the shell method. So what is the shell method? Here's basically what it is. An alternative method for finding the volume of a solid of revolution is called the shell method because it uses cylindrical shells. Okay? A comparison of the advantages of the disk and the shell method is given toward the end of the section, so don't sweat that yet. Consider a representative rectangle. Now that we're talking about this rectangle right here. Length H, width W. Okay? Now, the average radius of that is given as P. Why they chose P, I'm not really sure. The inner radius of this is P minus half that W, and the outer radius is P plus that half that W. Okay? Now, this rectangle they have here, H by W. Now remember, W is pretty small, but the area of that rectangle is H times W. Now, what we're going to do to get the volume of that shell that you get by rotating this rectangle all the way around, okay, that volume would be the area that you just did, H times W, times, and how far did it go? How far did the H times W go? It went around that shell. Well, that shell had a radius of P, and does anyone know what the circumference of that circular space was there? As you go all the way around that shell, that circumference is 2 pi r. 2 pi r, that's the, now, pause just a moment here. I want you to imagine something. Imagine you have a pair of scissors or shears or something. You can cut this cylinder here right along that H. Cut it all the way there. Now, and make a nice smooth cut so the thickness is still W. Now we're going to take that H and it's in a cylinder now, we're going to flatten it out. Okay? Now you have a thin wafer, thickness H, thickness W, width H, but now the circumference of that circular area there, that's now your length. Oops. And here's Morgan's iPhone is coming in. Oops, I can't do it there. Morgan's iPhone. So here comes Morgan. All right, good deal. Now let's see, we're up to 13 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Got it. Okay. Okay, you see what we do? We take that shell, flatten it out, and now it becomes a rectangular solid of thickness W, of width H, and of length 2 pi r, where the r is this P. You probably can't see the P right now because that stupid box, the box is in front of it. Can you see that P there? Anybody? Now it's fading out. You can probably see it. There is the radius of that circular shell, and when you flatten it out, that becomes the length of a rectangle. Okay? So R is the distance between P is the distance between the area of revolution and the center of that. My box is in the way, I can't see it. Let me see if I can move this box any further down. Yeah, well, I can't. It goes right back up. The center of the rectangle. Okay? Or center of revolution. All right. So, what was the volume of that? It was 2 pi P times H times W. Guess what? We're going to let the W go to dy or dx, depends on whether it's standing up or lying down. And then you have that you're going to integrate. Okay? Of course, you'll need to get the P in terms of y and the H in terms of y. That's going to be the big issue. Okay? I can't get the thing to advance until I touch the screen. When this rectangle is revolved around the axis of revolution, it forms a cylindrical shell or a tube of thickness W. We talked about that. To find the volume of that shell, consider two cylinders. The radius of the larger cylinder corresponds to the outer radius of the shell. The radius of the smaller cylinder corresponds to the inner radius. Because P is the average radius of the shell, you know that the outer radius is P plus W over 2, inner radius is P minus W over 2. We set all that, and it's absolutely ridiculous to have you fiddle around with those fractions. You really are never going to need them. Okay, we'll get to that later. So the volume of the shell is the volume of the outer cylinder minus the volume of the whole. Okay, so that's pi times, and this is the hard way to do this, pi times P plus W over 2 squared times H minus P times W minus W minus P minus W over 2 squared times H. And that gives you, if you went through, squared those ugly looking fractional binomials and multiplied it out, they get you 2 pi P HW, which is exactly what I said. If you just flatten that out and imagine the radius to be P, not P over 2 or P plus H, just P, okay? That's what you get. 2 pi P, that's the circumference of that circular shell, H is the width of the circular shell, and W is the thickness of that circular shell, okay? There you have it. It's 2 pi times the average radius times the height times the thickness. That's it. You can use that formula to find the volume of a solid of revolution. So why did they even introduce the W's over 2's, subtracting them, adding them? They all disappear. Okay? For instance, the plane region here, in this figure here, it's a triangle. Okay? And that plane region is revolved around a line to form the indicated solid. Now that does look like a Christmas tree stand lying on its side. okay? Okay, because you got a solid tube in the middle here where that C is, okay? So, consider the horizontal rectangle of width delta y. I told you that's what it was going to become. What they were calling W is now delta y. The length of this is we have to write as a function of y. It's going to be h as a function of y, okay? Times, and then you're going to have 2 pi p, I wish they'd call it r, 2 pi p, but p needs to be a function of y, okay? So, we're going to consider a horizontal rectangle of width, blah, blah, blah. This generates a representative shell. Oh, here's Houston. Let me get Houston in. I didn't see that, okay? Houston's here, good deal. All right. Welcome back, Houston. Okay. Has anyone else added that I didn't see? Okay, because this thing blacks out the names, and when it fades away, sometimes I can tell who it was. So here is the element of the volume, the delta V we'll call it, is 2 pi times that radius function times the height function or length function times your delta Y. That's going to disappear after a while, fade back out. There is your representative volume. So all we're going to do is integrate that if this thing ever gets out of the way. When you integrate this side, you just get V. You integrate this side, you don't have to include the 2 pi. Do the integral here, P of y times H of y times dy. Okay, and it won't advance until I touch the screen. Did I touch it enough? Yeah, there it goes. You can approximate the volume of a solid by n such shells of thickness delta y. The height, you have to figure that height as a function of y sub I, and the average radius as a function of y sub I. Then the volume of the solid, will be the summation from I is equal to 1 to n, 2 pi, that can come on the outside if you want it to, P of yi times H of yi times delta y, okay? And the two, like I said, the 2 pi can come on the outside. The summation of I is equal to 1 to n, however many shells you have, times P of y, H of y, times delta y. That approximation appears to be better and better and better as the norm for that partition, that's what the delta inside the two parallel lines shows, is approaching 0. That means n is going to infinity. So the norm is the largest of any of those partitions. So the volume of the solid is the limit as that norm goes to 0 of 2 pi times the summation I is equal to 1 to n of P of y, H of y, delta y. So that's the 2 pi, I'm going to wait till this box goes away, times the integral, replacing the summation. I can't get it to go away. It just hangs there. Oh, there it goes. The integral from C to D, I can't see the Z, P of y, H of y times dy. Let me get off this screen. Okay, so here's the shell method. To find the volume of revolution with the shell method, use one of the formulas here. If you have a horizontal axis of revolution, it's going around something parallel to the horizontal axis, then the volume would be 2 pi times the integral from C to D of P of y, H of y, dy, because your deltas would then be dy's. Now remember, in the disk method, your deltas were the same as your axis of revolution, okay? Not with perpendicular to the axis of revolution. Here, the axis of revolution is also is parallel to the x-axis. Okay, I said it backwards. The dy's going up this way are going along your axis that's perpendicular to the axis of revolution. I guess that's how I need to say it. Okay, we got too many axes in there. But for a vertical axis of revolution, you need to take a dx all the way around there, and then get your radius function and your height function as a function of x, not of y. So they like to use a to b to be your x's. So if you had, this looks like the same shape here, okay, the same shape here, and you're revolving this around the x-axis or something parallel to the x-axis, then you take a dy, and then you get your h as a function of y, your radius as a function of y, and then of course your dy is a y. If, however, that same one is going around the x-axis, or I mean something like the y-axis or parallel to the y-axis, then you express your h, the height of that rectangle, as a function of x, the radius as a function of x, and then of course your dx will be your thickness. Okay, now here's example 1. This is over on page, bottom half of page 466. Find the volume of the solid of form by revolving the region bounded by y equal y minus y cubed and the x-axis between when x is going from 0 to 1, but you're revolving that around the y-axis. Okay, now let's go to the y. Oh, here's Kerpa. Let me get Kerpa in here. Keep trying to move it with my finger and I can't do that. So Kerpa is here. All right, now we should be up to 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Got it. Okay. Okay. Now, let's go to I guess we got to go to the whiteboard, but the reason I'm sort of hesitant, I'm trying to decide whether I want to try to draw this and show it to you. Okay, there we go. All right, and let's clear that drawing. Does anyone need that any longer? That was the last example in 7.2. Can I clear it? All right, it's cleared. Now here's what we've got. Y is equal to x minus x cubed. Here we go. Y is equal to x minus x cubed. Okay, there's the function. And we're going to find the volume of the solid formed by that, by revolving the region bounded, okay, by that function and the x-axis about the y-axis. Okay, so let me try to do what I did before. Come up here to my draw screen. Okay, what in the world? Oh, there we go. Okay, now I'm going to try to draw a vertical axis. Not quite vertical, but kind of close. Okay, now we're going to draw a horizontal axis. Try to anyway. Not quite horizontal, but fairly close. Okay, now we're going to go from 0 to 1. So I have made a really big scale here. Okay, so let me go somewhere else here and just name this as 1. Okay, now obviously when x is equal to 0, your y is equal to 0. Okay, so the origin, well, I need to get out of this now. Come on. Okay, at x equals 0, y is equal to 0. I hope everybody's quit this. I don't know why it does that. Okay, x equals 0. If I hold it in one spot, it changes. Okay, so I can't draw, maybe if I draw a little circle there, will that work? Okay, it's there. I can't draw a dot because it changes. When x is equal to 1, y is also 0. And I can't get it to draw. So let me try again. Okay, it's also 0. Now, let's see what happens in between. Like maybe 1/2. When x is equal to 1/2, let's come over here, y at 1/2 is equal to 1/2 minus, and I think I would be better off, that would be 1/8, right? 2 times 2 times 2, yeah, that's 1/8. Okay, and that would be 4/8, that would be 3/8. All right, so up here, if this is indeed something, does that look about 1? So 3/8 would be somewhere along in here. We'll make this 3/8 if I can get it to right. Okay, now, so at 1/2 you're around 3/8. Okay, you can plot other points, and obviously that one's not plotted well. Let me try to draw, and this is really going to be a joke. Okay, let me try to draw what they did in the text. It came up like this. Yuck, that's not good. Something like that one. Okay, I know that's not very pretty, not very precise, not very accurate, but let me get rid of that. Let's just say that's it. It's a rude attempt at a draw. Okay, now we're going to rotate that volume formed by that region, y is equal to x minus x cubed, and the x-axis, that's down here, there's the x-axis, about the y-axis. So this is going around like this. Okay, so what we have here is half of the donut, isn't it? Well, half of a bagel maybe. Okay, no hole in the middle, just okay, something like that, I think, in terms of food. Okay, now obviously if you're going around like that, we need to do a delta y, and let me just take, a delta x, okay, because it's going around the y-axis. So here's our delta x, only I'm going to call it dx. I like to go straight for the integral. Okay, now let me give you a good hint here. What is the radius of this revolution here? That's just your x, as x is going from 0 to 1. So there's r as a function of x, it's just x. Now, what's a little, well, that's not tough at all. What's the height of this? Well, the height of that is x minus x cubed. There's the height. Okay, so this doesn't look too bad at all. Okay, if I can get my pen to show up somewhere where I can use, okay, here we go. All right, so here we have the volume would then be, remember, the radius is multiplied by 2 pi. Okay, the radius is x. The height is this thing here, x minus x cubed. Does everybody see this? And then the thickness is dx. And we're going, x is going from 0 to 1. Okay? Well, that integral will be, I don't know why I can't write horizontally, but I can't. 2 pi, I tried, I really did, times, okay, we probably need to do that one more time, 0 to 1. Okay, let's multiply through. That would be x squared minus x to the fourth, right? Dx. Okay, so this will be 2 pi times antiderivative of x squared. I swear this is such a pain in the neck, or some other body part. Okay, x squared up x cubed over 3 minus antiderivative of x to the fourth, x to the fifth over 5. And we evaluate that from 0 to 1. The calculus is the easy part, isn't it? That's 2 pi times, plugging in 1, it's just 1/3 minus 1/5. Plugging in 0, you get absolutely nothing. Okay? And what is that? Well, that is 5/15 minus 3/15 is 2/15, so that would be 4/15 pi. At least that's what I hope the answer is. And look at that, the book got it right. 4/15 pi. Now, was there anything about that procedure that was baffling to you? Did I lose you somewhere in that? Or did that make sense? Okay, I hope that made sense. Let's go back to the PowerPoint and you can see how they did it. I keep trying to do that with my finger and I can't. Okay, so where was the PowerPoint? 7.3, that was it. Okay, there we go. And we'll go back to current slide. All right, there we have it. Find the volume of the solid formed by revolving the region bounded by, oh, and they may even draw the picture for us. I'm so dumb. Yeah, there they have it drawn for us. I didn't have to hold up the book. Well, I don't think I did. Okay, anyway, there's your curve. Because the axis of revolution is vertical, going around the y-axis, that's obviously vertical, we'll use the vertical representation of a rectangle, okay, and the little delta x, I wanted to go and call that a dx, is your thickness. The height of that is merely the function value, okay, and then the radius of that, the p of x, is just x from 0 to x, okay, as x is going from 0 to 1, okay. So there basically is your integral already set up for you, okay. The distance from the center of the rectangle to the axis of revolution is x. That's how far out you are. The height of the rectangle is that function value because you're going from that down to the x-axis. So that's going to be x minus x cubed. And because x ranges from 0 to 1, the volume would then be 2 pi, because that's what you multiply by the radius function, p, 2 pi p times h times your thickness dx. That's it. And that'll be the integral. The 2 pi can come on the outside. The integral from a to b, which in our case is from 0 to 1, of p of x, which in our case is x, and times h of x, which is that function value, x minus x cubed. Okay? So that's what they did. They plugged those in. 2 pi times the integral from 0 to 1 of p of x is x, h of x is x minus x cubed, and your dx is dx. Okay? Multiply the x through, distribute the x, and you get... Now, why in the world they changed the order, I don't know, but they did. So that'd be 2 pi times the integral from 0 to 1 of a minus x to the fourth plus x squared. I liked it perfectly fine, x squared minus x to the fourth dx. Doesn't matter when you go to integrate. It's 2 pi times minus x to the fifth over 5 plus x cubed over 3, evaluated from 0 to 1. Plug in the 1 and you get 2 pi times, I've said 1/3 minus 1/5. They said minus 1/5 plus 1/3. Doesn't matter. When you do the 0 on it, you get nothing. Okay? So the difference there is 2/15. Multiply that by 2 pi and you get 4 pi over 15. Same thing we did. Any questions? All right. Before we get comparison of the disk and the shell method, we need to do example 2. And it looks like that's going to be totally on the white page. So let's go whiteboard. Okay. Now let's go over here and clear off the, does anyone need the last example still up here a little bit longer? I hope not. Okay, we'll clear it. Okay. Find the volume of the solid formed by revolving the region bounded by the graph of, okay, x is equal to, wait, Morgan must have had to go out and come back in. So let me let her back in. Yuck, get that out of the way. Okay. All right, Morgan's back in, but she was already here before, wasn't she? Yeah, I had her here before. Okay. So let me get my book over here so I can read it better. It's just so heavy to read, to hold. Find the volume of the solid formed by revolving the region bounded by the graph of x is equal to e to the minus y squared. So, oops, I can't write on the board. Okay, x is equal to e to the minus y squared. Okay, there is your function. About the y-axis between 0, y going from 0 to 1. No. And the y-axis between 0 and y equals 0 and 1, and the x-axis. Now this one, basically I have to draw, and I'm so sorry to have to do it. Okay, so let's go up here and get our straight lines again. Let's just imagine that's a vertical line. No, it's not very, is it? Okay, and let's just imagine this is a horizontal line. And that's not very horizontal either. Okay, and the y-axis. Well, this is the y-axis here, so let me get my draw pen here. And this will be our y, this will be our x, and we're going from 0 to 1 on y. So where's my pen? There it is, 0 to 1. We'll make that 1. Okay. Now, it says find the volume of the solid formed by revolving the region bounded by the graph of this. Now we have to get the graph of that. So let's first start with y equal 0. Y is equal to 0, x is equal to 1. Well, let's just say there's 1 on the x-axis. So there's the point x equal 1, 0. Okay? Let's move up to where y is equal to 1. And then you would have e to the minus 1. Now, I don't have a calculator. Well, I mean, I do have a calculator. I don't know that on top of my head. So let me log in. Oops. Yuck. Okay. Have to turn my phone sideways. Y'all know how to do that, right? And what we have is x is equal to e to the minus 1. So what I want to do is a minus 1. On my phone I have to do a 1 plus minus and then do the e to the x. And that gives me 0.36788. Okay, so when y is equal to 1, So, oops, I can't write on that. So x when y is 1 is equal to, or approximately equal to 0.36788. Now that's way too many digits. I can't draw with that kind of precision, but just to get it out there. Okay, so when y is equal to 1, there's y is equal to 1, this will be a little bit more than 1/3. Does that look about right to you? I can't. This is so frustrating. Why in the world that does that? So let's say something about right there. Okay, now if you wanted a value in between, say when y is 1/2, we do x equal e to the minus 1/4. Okay, so let's make that 0.25, negate it, and then do e to that. And that would be about 0.6. Okay, so that would be somewhere over 0.6 would be somewhere about here. So at 1/2 you'd be somewhere here. That's so frustrating. Okay, 0.6 would be, okay, right about there. All right, now this is just going to be a really rough, ugly approximation. It's starting here and going down to there. That's not anything close to what the book has, but let's just say that's it. Okay, now, and we're going only as far as y equals 0 to 1, so this is the only region. Oh, and we're revolving this about the x-axis. So this shape between there and there is revolving around the x-axis. Okay, now let's take a cylinder. Let's take a delta y right here. There's your delta y. Okay, now what's the radius? The radius is the distance from the center of revolution. Well, that's the x-axis. That's just y. So your p of y is y. Okay, and your x is your height. The height here from here to here is just your x value. And the x is e to the minus y. So your h here is equal to e to the minus y squared. I said minus y, but it's minus y squared. Okay, and your p, this is your p of y here. I didn't write it because I didn't want to try to struggle with it. P of y is equal to y. Okay, so we can write down our handy dandy little integral here. The volume is equal to 2 pi times the radius, so that's 2 pi. And I keep calling that the radius. And the y, because your dy's here, is only going from 0 to 1. They gave you that in the problem. Okay, of y times your h is e to the minus y squared. And then your thickness is dy. Okay, there we have our integration. Now, this is probably not quite as simple as it's been, but it's not too bad. Let me get this off of my lap. Okay. Now, how would you approach that integration? How would you find the antiderivative of that? It's a definite integration, so you're not going to stop at an antiderivative. You're going to evaluate it. Anyone come up with a method? Again, if nothing is obvious, pick you the innermost part of the most complicated part of that problem. Well, I would say definitely the e is the most complicated part of the problem. The innermost part of that would be, say, a minus y squared. So let's let our good old u equal minus y squared. Okay. I don't know what's making the dinging noise. I have no idea. Okay, then, always if you have a let, follow it with a then. Then du, that's the then that you follow with. Anyone tell me what that is? I hope you all are doing something. I can't hear anything. All of you have your microphones off. That's minus 2y dy. Right? If you have any objection, if you see I'm making a mistake, please say something. Okay? Well, up here we have, there's a 2. Well, but that's on the outside. We have a y dy. We want this to be a y dy. So what we're going to do here is divide by negative 2. So we have to divide the du by negative 2 as well. Okay? So this becomes the integral. I should have put my 2y here, 2 pi here. Now, we're dividing by negative 2, so I'll put the negative 2 here, but of course the 2's are going to cancel out. Now, here's an issue, folks. We move from y's to u's. These limits here were limits for y. What we're going to have now is a du, so we need limits for u. So let's plug those in. When y is equal to 0, u is equal to 0, right? Okay. When y is equal to 1, u is equal to negative 1. Well, whoa, folks, I don't really like that, but we'll deal with that in a minute. Okay. And then what we have the negative 1/2 out front, so the y dy over negative 2 is du, and this is e to the u du. Okay, now the thing I don't like about this is you have your integrand, the limits reverse. So to get them back into the right order, we're going to have to negate this, but that would be wonderful because I didn't like that minus sign anyway. So that leaves us pi times the integral from minus 1 to 0, flipping the things to that, e to the u du. Now, I think everybody, I hope everybody, can tell me what the integral from e to u du is. Antiderivative of e to the u du. Please, somebody, tell me. It's e to the u, my favorite function of all time, because you don't change its integral or its derivative any. That would just be e to the u, and that's evaluated from minus 1 to 0. Okay, so I'm going to try to do that. That's going to be pi times e to the 0 is 1. Anything to the 0 is 1, except 0 to 0 is undefined, minus e to the minus 1. Okay, now if you wanted to approximate what that value was, hold on just a minute, let me get my handy dandy calculator, actually telephone, which has a calculator on it. I think I'm going to have to turn it sideways to accommodate that. So what we have is, you can do it the way it's written here, pi times, open parentheses, 1 minus, and then we're going to put a 1 negate, and then raise that to the e, and then close my parentheses and press equal. And I get something pretty close to 2, okay? 1.986. That's what the book got. That's what I got. So that is the answer. Pi times 1 minus 1 over e. That's another way to express it. plug my phone in before I run it too low. Okay. All right, and that was another way to express it. I didn't write it that way, but you could. You could have written this as pi times 1 minus 1 over e. That, I think, is how the book did it. Okay. Which you could write yet another way that the book didn't, but it's perfectly legitimate. Equal pi times e minus 1 over e. That to me is a little more complicated, but at least it's a ratio, but whatever. Okay. All those, and the answers are the same. Any questions on that one? All right, to go back to, I keep trying to do it with my hand because I'm so used to doing that. Let's go back to the PowerPoint. And that's that one. Okay. We'll go back to current slide. I'm going to get used to this after a while, maybe a year or two. Oh, I'll be retired by then. Never mind. All right, so let's move on to comparison of the disk and the shell methods. Okay. Y'all can read that, can't you? They haven't blocked it out. Hopefully so. Okay. Now, the disk and the shell methods can be distinguished as follows. For the disk method, the representative rectangle is always perpendicular to the axis of revolution. Again, I have no idea why the beeping is happening. Maybe my pad is hitting a key. I don't know. The disk and shell method can be distinguished. Okay. This method, the representative rectangle is always perpendicular to the axis of revolution. That makes a circular disk. Whereas in shell method, the representative rectangle is always parallel to the axis of revolution. That makes a shell. Okay. Now, they've shown it here. I don't know if this is particularly useful to you. If you're revolving around the y-axis here, okay, then the disk method, or in this case the washer method, you would rotate this rectangle all the way around and see the rectangle is perpendicular to the axis of revolution. Okay. Now, frankly, I guess it's just the way I think. I think the dy's are going up and down. You're going around y, and the dy's are going around there. So that's how I think of it. You're going around the y-axis and you're using dy's. Those are the same. Okay. If you have a horizontal axis of revolution, like this one, going around the x-axis, well then obviously again you've made your dx's are going around the x-axis. Okay. You have everything in terms of x. Okay. Now, in the shell method, you have a vertical axis of rotation, but your rectangle is also vertical. You can think of it that way, but it's rotating your you've got a dx here going around an axis parallel to the y. So the book phrases it one way, I phrase it the other way, but it's saying the same thing. If, however, you're going around the x-axis, or some portion of the x-axis, like here, something parallel to the x-axis here, but you're doing a shell that's in dy, then that's going to make a shell that goes around the x-axis. If you're going around the y-axis here, that same rectangle over here going around the y-axis makes a washer as you revolve that around the y-axis. That makes a washer there. This makes a shell as you go around the y-axis. Okay. So here's example 3, which should be on page 68. Okay. How are we doing on time? Okay. We go till 2:20, so we got plenty of time. 2:25. Okay, example 3 here. Find the volume of the solid formed by revolving the region bounded by the graphs of y is equal to x squared plus 1, y is equal to 0, x equals 0, and x equal 1 about the y-axis. Now that's enough things to be revolving, isn't it? So let's go to the whiteboard. Okay, and clear off the stuff we've drawn before. Okay, and try to set up an axis here. This is always fun, isn't it? Okay, where are we? Here we are. Let's just do a vertical axis here. For some reason, it's not drawing a vertical axis. Okay. Okay, this is nuts. Let's erase that, whatever it was. Whatever that was, let's get rid of it. We don't want it. Let's try that again. Okay, we start here. There we go. Let's just imagine that's vertical. It's not. And let's just imagine this one's close to being horizontal. It's either fairly close or it's not showing up. Okay, so may have gotten it right. Fairly close. All right. So let's find the volume of the solid formed by revolving the region bounded by the graphs of, and by the way, even if you don't have this textbook, okay, you can go to larsoncalculus.com and see an interactive version of this kind of an example. In fact, I think it'll be this exact example. So here's the first thing. Y is equal to x squared plus 1. Where will I write that? Let me write it here. Oops. I want to get my draw pen back. Okay. So y is equal to x squared plus 1. Now, why in the world control shows up, I don't know. Okay. Now, let's plot a few points. Well, let's get the rest of it down. Y is equal to 0. Y is equal to 0 is the x-axis. Okay? X equals 0, that's the y-axis. And x equal 1, that's over here. Let's just call that, let's see, let's call this 1 and that 2. Okay? Then this will be 1. Okay, so x equal 1. So when x is equal to 0, y is equal to 1, so you're right here. When x is equal to 1, y is equal to 2. That's why I put the 2 there. And this is simply a parabola. Sort of going like that. A pretty ugly parabola. So here's what it's bounded by. I'm not going to bother getting my straight lines again. This is the region we've got. Now what is that doing? About the y-axis. So this is going around this way. Okay. Now, here's our dilemma, folks. And I'm hoping some of you are saying, haven't we seen this before? And the answer would be yes. The last time we did it, we just did the bottom part of this is a solid cylinder of radius 1, and the top part here was a washer, series of washers, okay? And we did it. Now that we know the shell method, what we can do, and I think it works out perhaps a little easier, is do our dx's here. Do a shell like this. And the reason this is easier, you only have one set of thing. You're going, and if you're doing a dx here, but you're revolving it around the y-axis, that's going to make a shell. So you know your integral then, you can almost write it down. The volume that you have is going to be, since it's a shell, it's going to start with 2 pi times the radius. What's the radius? Okay, the radius is your x value from 0 to x. So that's the integral of x, that's the radius, 2 pi x would then be your circumference, times the height here. Well, the height here is just exactly your function there, x squared plus 1. If I can get my pen over here to write it, x squared plus 1. And then your thickness is your dx. Okay, there's your integral. Well, almost. Let's clean it up just a tad. 2 pi times the integral of x cubed plus x dx. And the x's are going from 0 to 1. I could have put them up here too. Okay. Okay. The integration is the easy part. Setting it up, that's a little more. The integration is pretty easy. Antiderivative of x cubed. Hopefully all of you are yelling into your silent mics, x fourth over 4 plus antiderivative of x squared over 2, evaluated from 0 to 1. Okay, and that's going to be 2 pi. I can do that part. And then what you have here is 1/4 plus 1/2, which is 3/4 times 2 pi. That would be 3 pi over 2, I believe it is. Yes, that's it. 3/2 pi. Okay. And if you glance back, you will see that indeed that was what we got before. I'm pretty sure. Let me just go back and see. Ah, there it is. Example 4. That's exactly what we got. Okay, when we did it, the solid at the bottom and washers on top, 2 parts, doing them up. One part was pi, the other part was pi halves. Added together gives you 3/2 pi. This one part, do the shells all the way around, you got it knocked. And it's pretty easy math too. Does that make sense? Well, let's watch and see how they did it. Sorry. Excuse me just a minute. It's been a very busy morning so far. I had a meeting with a Zoom meeting with Montgomery for the first hour, and then I was trying to catch up on emails and tests and papers and homework and stuff like that for the next hour and a half, and then try to cram down some lunch. So I'm kind of going kind of ragged here. Okay, there was example 3. Any questions on it? What I was going to do then is go to oh yeah, I have it. 7.3. We'll go to present slide, and here's example 3 that we just did. So the solution, they said the washer method requires 2 integrals. You could do one without doing an integral. We've already done it. But it has a disc at the bottom and washers at the top. And if you did that, you would have those. We've already done that. That was example 4 in the last section, 7.2. Yeah. Okay. So I'm not going to rehash all that, but you got pi plus pi halves, and that gives you 3/2 pi. If you do it the shell method, it requires only one integration, because your shells here are going from here to there all along here. There's only one set of integrations here, okay? Because the axis of revolution, I wish they'd have drawn it here, is like that, okay? And you're doing those shells around. What's the height of that? The height of it is your x squared plus 1, the function value, okay? What's the radius of this? X. And your dx is your thickness, okay? And that gives you the integral you need to do, 2 pi times the radius times your height times the thickness. And there it is. 2 pi times the integral from within your limits. For us, it's going to be 0 to 1. The radius function is simply x, and the height is your function, which is x squared plus 1. Okay? Plugging those things in, 2 pi times the integral from 0 to 1, x times x squared plus 1 dx. Multiply that through, well, they just skipped a bunch of steps, didn't they? Went straight to that, and that gives you 2 pi times 3/4, which is 3/2 pi. You can't see it, or I can't see it because my taskbar is in the way, but it's 3/2 pi. Any questions on that? All right, are y'all picking up the vacuum cleaner noise outside, or does that bother you? Anybody? Obviously not. Okay, so let's go on. Whoa! That's the end of the slideshow, and we still have examples 4 and 5. So let's see, do we have time? I think we do. Let's see, we go, yeah, 2:20. Yeah, I think we got time. So let's go somewhere here. Oh, I can't do it. I keep trying to do it with my finger, and I can't do it with my finger. Let's go to our whiteboard. And let's clear that out of the way. Now, example 4. A pontoon is to be made in the shape shown in figure 734. Now this one they don't have on the slideshow, so here's what it looks like. Okay, there's your pontoon. Okay, now that's for those who may be fisher people. You may have been on a pontoon boat before. These are the floats that hold the boat up. Okay, that's usually what a pontoon is. There may be other applications. Okay, the pontoon is designed by rotating graph of, I want to write on the board, y is equal to 1/16. No, I was, heck. Okay, let's try it again. Let me read the book well. 1 minus x squared over 16 okay, when you allow the x to go between -4 and +4. And you're doing about the x-axis, no. Yeah, about the x-axis. This is not a very smoothly writing thing. I'm writing a lot smoother than the jerking that's going on the slide. Where x and y are measured in feet. Okay, we don't need to know that. Right, we are. The answer is going to be in cubic feet. Find the volume of the pontoon. Okay, so here is a hint. Okay, let's go back to our picture to verify the hint. Okay, I may not have shown the entire picture, but let's do it. Okay, There is the pontoon. Underneath it is the graph of that function I just did from -4 to 4. Notice that's symmetric about the y-axis. So to find the volume, all we have to do is take the volume between 0 and 4 and double it. Okay? Now, do I need to draw that? It probably would be helpful. No. Back off from that. Let me draw the thing for you. So I held up the book, but that's not as good as seeing it. Okay? So, yeah, I keep hitting the screen. Okay? All right. Let's just try to imagine that's a vertical line. Hey, it's not as bad as some have been. And let's just say this will be approximately a horizontal line. That's worse than before. Okay? Now, we're going from -4 to 4. So let's tick off a few points here. Okay. 1, 2, 3, 4. I don't tick off very even points. 1, 2, 3, 4. So here's -4. And why it draws some lines fine and others it doesn't. Okay, I don't know. There's 4. Okay. Now, this is a parabola opening downward. Okay, that's why the minus x squared. Okay, and it doesn't rise very high because when x is equal to 0, this is 1. So that's just going to go to about here. Well, yuck. Let me first move this back. I don't know why it does what it does. Okay. Now. Okay. So y is equal to 1 to 1. Okay. So this is going to be, now this is the awful part. Okay. Let's try to get this as even as I can. Sort of, oops, overshot. A parabola that does something like that. I've got too long over here and something like that. Now that's not very pretty. Okay. Can I do any better? I don't know. Let me try. I'm not going to waste a lot of time trying to do better. No, that's worse. Well, you get the general idea. It's a pontoon. Looks like a very elongated football. Okay, very elongated for all the football fans. Okay, so what's the best way to find the volume? Do you think, and this is made by rotating this around the x-axis. I drew the bottom around the x-axis like that. Now, do you think a disk would be wise? Absolutely not. Okay, your disk would be, well, wait, let me see. I still don't think it would be wise. Okay, we got this in terms of x's, so we'd like to take dx's if possible. Okay, so that would be our choice, is to take a dx. Well, you can get this volume by, okay, now again, what I said before is almost going to work here too. If you do this, just this one, where x is going from 0 to 4, and take this around the y-axis here, okay, that would be your axis of rotation. That's going to make you a shell, right? Okay, now you've got this in terms of x, you got this in terms of x. Guess what? Your radius is x, as x goes from 0 to 4. Everything's that. And by doing this, that height there, just the x, then you get the top half of that pontoon. Double it and you get the bottom half of the pontoon. So that's, I think, how we need to proceed. Okay, so your volume is going to be since we're using a shell method, 2 pi times the integral. And the integral, since we're doing dx's, is going from 0 to 4. You don't have to do minus 4 to 4 because you're doing your circular, you're rotating. That takes care of that. The rectangles that you're rotating only go from 0 to 4. And we're only doing that height, and we're going to double it. So let's go on and go over here and change that 2 to a 4 because we're going to double it. Okay? All right, so let's make that 4 pi. 2 pi r for our circumference, but double that because we're doing the bottom half as well. Okay? Now, your radius is x, and your height is 1 minus x squared over 16. And then you're multiplying that by your thickness, dx. There's your 3 dimensions. The circumference, the height, and the thickness. Okay? Multiply them together. The reason we double is to get the bottom half of that pontoon. Just going from 0 up to the top gives you the top half of the pontoon. The bottom gives you, the doubling it gives you the bottom. Okay, so the first thing we're going to do here is 4 pi times the integral from 0 to 4, multiply through, and that gives you x minus x cubed over 16. Yuck! I rested my hand too heavily there, and that's going to be your dx then. Okay? Now let's do the integration. It's going to be 4 pi times antiderivative of x. I can hear all of you screaming x squared over 2. Very good. Minus, and that'll be x4 over 4. So x to the 4th, and you already had a 16 down there, and put another 4 down there, that's 64, if the pen would write. Okay, and evaluate that from 0 to 4. Oh boy, a little bit more to the evaluation. I loved it when it was 0 to 1, didn't you? So that's going to be the 4 pi, that's out front. Don't forget it, it's there. 4 pi times, and when you plug in a 4 for the x, you get 4 squared is 16. 16 over 2 is 8. Minus. Now, what is 4 to the 4th power? Well, 4 times 4 is 16. Times another 4 is 64. And times another 4, who cares? The 64 will go into that 64, and that just leaves you another 4, factor of 4. Okay? So this looks like it's going to be 16 pi. 8 minus 4 is 4, times 4 pi is 16 pi. Let's see what they got. Oh no. Okay, I've done something dumb here. What is it? Now wait a minute here. Where did they get that? Oh, they're doing a disk method. They did exactly what I said. Oh no, I misread it. Sorry about this. About the x-axis. Okay, I drew it right, but then drew it up here as if it's going around y. I'm sorry. I did the wrong problem. Let's clear this out of the way. Sorry about that. Okay. Really dumb. Sorry. I should have left some of it there, but I didn't. That was inexcusable. I had it drawn right the first time and then changed it. So what we have is 1 minus, no, y is equal to 1 minus x squared over 16. Okay, I'm sorry. I had it going the other way and that didn't make sense. Sorry. Still seems like that should have worked, but that wasn't what was going on. And that's from, I keep wanting to write on the screen, from -4 to 4. Okay, and we're going about the x-axis. I think I wrote that before. Yuck! This is so aggravating. And the thing is, if I go too fast, it doesn't write. If I go too slow, it quits writing. It is aggravating to me. I think it may have something to do with pressure or precision or something. We may need to change that. About the x-axis. Okay, and they say y is measured in feet. Okay, find the volume. So, I'm sorry, I should have left some of this up here, but I was so frustrated with it. I erased too much. Okay, so let's give an approximate vertical line, which is nowhere close, and an approximate horizontal line, which is nowhere close. Okay, and then tick off my points. I think I prefer to tick them off here. So you have 1, 2, 3, and 4. 1, 1, 2, 3, and 4, and 1 down here. Okay. Now this is where I tried to draw the thing before. Maybe having just a tad more luck with it here. Something like that. And something like this. There's your pontoon. And this thing, I shouldn't have drawn that. It's going around the x-axis. I drew that before and then put it around the y. I don't know why. Okay. Since everything is measured in x's, we'd like to take our dx. Okay, but a dx is then going to be a disk. Okay, now if you remember back what the disk method was, the volume of that disk, the thickness is dx. I can tell you that one. The radius is the height of that, which is exactly this. Where is it? There it is. That is the radius. Okay, so what is the volume of that disk? The volume of the disk is, if I can get it to write, V is equal to, okay, pi r squared, and the r is your radius, so this is 1 minus x squared over 16 squared times your thickness. That's your disk method. And the disk is going from 0 to 4. Now wait a minute. I thought it was -4 to 4. But remember, and this is what I started off saying, this side exactly the same as that side. Maybe my picture doesn't look like it, but it is. So we're going to be doubling this. Okay, double the volume from 0 to 4, and you got it knocked. Well, the first thing that we got to do here is square that binomial. So this is going to be 2 pi. Now that 2 pi is not because it's a cylinder, it's because you've doubled the disk. Okay? 2 pi we'll still keep the integral from 0 to 4. Now we got to square that binomial. 1 minus 2 times x squared over 16 would be x squared over 8. Yuck, it did it again. And again. X squared over 8, okay, plus x to the 4th over square of 16. I'm just going to write 16 squared, okay? It's 256, I think, but why would it not write? Okay. Whew, I'm fighting with this thing, and I don't know why it's being so stubborn. dx. All right, so let's do the integral. 2 pi, that's the easy part, okay? Antiderivative of 1 is x, minus, and this will be an x cubed over 24, plus, oh man, x to the 5th, and tell me, I think 16 squared is 256, and then we're going to multiply that by 5, and that's 1280, I think. I hope. Okay. Plus x to the 5th over 1280. One of my favorite numbers of all time. Okay, that's what you get from the 5 times 16 squared. And we're evaluating this from 0 to 4. Okay. Now, that, believe it or not, will not be as bad as it looks. 2 pi. Certainly with the 4 in there, that's just a 4. Minus. Now, 4 cubed is 64. Okay? But remember that 24 is 8 times 3. Okay? Well, 8 is 4 cubed. So you got 4 cubed over, no, I'm sorry, I said that wrong. Sorry, back off. 4 cubed is on top. On the bottom you got 4 times 6. So it's a 4 squared over 6. 16 over 6, and that would be 8 over 3. So I think that's 8/3. Now you can check the math, but I think that's right. 8/3. Maybe wrong. Okay. This next one's going to be even worse. Okay. Now remember we had a 4 to the 4th power in the denominator. And now we got a 4 to the 5th power in the numerator. So that leaves us a 6 over 5. I'm sorry. A 4 over 5. And again, you can check my math on that, but I believe that's right. Because you had 4 to the 5th here, and you had 5 times 4 to the 4th here. That gave us a 4 over 5. I believe that's right. Now, let's see if this does add up right. If it does, it'll be a miracle. All right, least common denominator. Let's come over here and do the 2 pi times, least common denominator is 15. So 4 is 60 over 15 minus 5 times 4 is 40 over 15 plus 12 over 15. Okay, let's see if we have any chance of coming out reasonably. 2 pi times, well, 60 minus 40 is 20 plus, that's 32/15. That is an ugly 5, okay? And that's going to be 64 pi over 15. Is that what they got? 64 pi over 15. Good for them. Okay. Sorry about that. All right. This method was the way to go on that one. Did lead to some pretty hairy numbers, but they were all manageable. Okay. Does anyone need this left up here any longer? I'll be glad to leave it if you need it. Are there any questions over it? Okay. If not, I'm going to clear it out of the way so we can proceed to example 5. Find the volume of the solid formed by revolving the region bounded by the graphs of y, and where the control came from I don't know, y is equal to x cubed, okay, plus x plus 1. Sometimes it writes and sometimes it won't. Okay, let me pull this over so it's easier to read. So there's one graph, one function. Here's the second function, y is equal to 1. That's a pretty easy one. Y equal 1. The third one is x equal 1. And about the line y is equal to 2. Yuck! Okay, no, that's x equal 2. It came on when I was trying to read. It's x equal 2. Okay, for some reason the t didn't cross. All right, and they do show a figure here. Let me show you what it's supposed to look like, and then you'll laugh when you see me draw it. Okay? I can't even see this. That's that one, that's this one. Okay. That's what it's going to be looking like. We hope. Let's see if we can make it look like that. Okay? I don't think I need the book anymore, so I'm going to set it aside. It's too heavy to hold. All right. Oh boy, I probably will need the book. So again, let's do my axes using straight lines. At least I can make them straight. They may not be vertical, but they'll be straight. Okay, and horizontal. Come on, there we go. Still not quite horizontal, but we will live with that, I guess. Okay, now line y equal 1. Let me punch in some numbers here. And x equal 2. Okay, so let's do, say, well, let me go to my draw mode. Too hard to do them. So let's do 1, 2, 1, 2, 1, 2. I don't think I need them over here, but I'll do them in there anyway. Okay, now y is equal to 1 is this dotted line right here. Okay, x equal 1 is this dotted line right here. Okay, those are the easy parts. x equal 2 is this place right here. Okay, now, so we're going to need to tick off a couple more points in this direction. Okay, now, oh no, I'm going to do an axis up here. We don't need it down there. Okay, now what we have to do is draw the picture of this graph. When y is equal to 0, when x is equal to 0, y is equal to 1. So it's right here. When y is equal to, say, 1, you're 1 plus 1 plus 1, you're up here at 3. I didn't go far enough up, did I? Okay. So here we're at 3. Okay. So let me see if I find the volume of the solid formed by revolving the region bounded by the graphs of y is equal to x cubed, that one, y is equal to 1, x equal 1. Okay. Oh, okay. It's the portion that's in here. Somewhere right in there. This is the part right here between x equal 1, y is equal to 1 in that graph. Okay. That's what we're revolving around this line over here. Okay. Which means I think I drew that too far over. Sorry. Y'all let me get away with that. This is wrong. Whoa, where's my eraser? There we go. This is 3. It's x equal 2. Okay. This is what we're drawing it around. Whoops. It's supposed to be vertical. And this, we don't need it down there. Okay. So that means, and we had the 2 lines over here. Okay. So this one around this line is going to be right here. And this one around that line is going to be right here. So here is the other half of this. Okay. So this thing here is revolved around to make here. So this is revolved this way. So you get another Christmas tree stand, but this really big trunk tree, but a very small stand. Okay, that's what you get here. Okay. Now, it looks like to me, here we have our y as a function of x, so it would be advantageous as far as I'm concerned to do a dx here. So let me do a dx here. Yuck! I can't believe it just did that. Okay. I don't know why it's doing that. Okay. Here's the dx here. It's pretty crowded. There's your dx. Okay. Now, obviously, you're going to make a disk as you go around, follow that curve around there with that. So what's the height? The height is this thing minus 1, because your height is going from here, where your y is equal to x cubed plus x plus 1, to down here where y is equal to 1. So that is going to be the h function, and this will be as a function of x, is going to be x cubed plus x, because it's this thing minus 1. So the 1s would cancel out. What's your radius? Well, the radius is just, again, your x. So the radius function, they call it p, sorry, I'll call it r. the radius function p of x is just merely the x, okay? And then your dx is your thickness. So using the shell method, the volume would be 2 pi r, 2 pi, times the integral from, and where is the x going? From 0 to 1. Okay? And then x times h, or p of x times h of x, would be x to the 4th plus x squared. Seems like we've done that one before, dx. Okay? So that would be 2 pi times the antiderivative of x to the 4th is x to the 5th over 5 plus x cubed over 3, evaluated from 0 to 1. That's not too hard to evaluate. It's hard to write an equal sum, but it's not to. That'd be 2 pi times 1/5 minus 1/3. And write that in terms of 15ths. I think we've been here before. That's oh, wait, wrong. Okay, sorry about this. I was doing my radius from the y-axis. It's not from the y-axis. This is wrong. So let's get rid of this and this. I can leave that part. Okay. I don't know what that was. I'll get rid of that too. Okay. These things are hurting my ears. Okay. Got to go back and see what the radius function is. The radius is the radius of circular motion here. So you're going from here around to there. Well, this is 2. X equal 2 is the center of that circle. And, yuck. Okay. And the radius is 2 minus x. Do you see that? The radius is 2 minus x. Okay, I don't need the parentheses there, but the radius is about the line x equal 2, and 2 minus x would be that radius. 2 minus 0 would be, whoa. That's not right. Okay. Okay. It's 2 minus, I think it's 2 minus 1 minus x, which is rather strange. Yeah. It's 2 minus 1 minus x. So again, get out the eraser. Okay. Let's do a little more reasoning here. Okay, here's the center of the circle is this, 2. Okay. And this position here, of course, is x. Okay. But this length here is 1 minus x. Okay. And then add 1 to it, and you get 2 minus x. Well, that's what I got before. That's not making sense. Two minus, let me try that again. 2 minus a 1 minus x. That's what I'm saying, and I'm not getting the same thing. And let's see if that gives it to us. That would be 1 plus x. When x is equal to 0, now that's still not giving it to us, right? The radius, when x equals 0, should be 2. And when x equals 1, it should be 1. Yeah, I had it right the first time. It's 2 minus x. Because when x equals 0, the radius is 2, and when x equals 1, the radius is 1. What was wrong with my brain? I had it right all along and talked myself out of it. Okay. Yeah. Okay. So that is 2 minus x. That's your radius. Okay. So we got to multiply 2 minus x times x plus x cubed plus 1. So I'm going to come up here and do this because I don't have room below. Okay, and that's what I'm going to write down here. All right. Going to start with a 2x cubed, if my pen would write, minus x squared. I did this one times this one, this one times this one. Okay. Minus x to the fourth. That's this one times that one. And then plus 2x. Okay, that's pretty ugly. All right. I believe that's right. 2x cubed minus x to the fourth plus 2x minus x squared. Yeah, I think I got them all in there. All right, now let's do our antiderivatives. This will be x to the fourth over 4, which would be, but you got a 2 in front of it, so x to the fourth over 2 minus x cubed over 3 minus x to the fifth over 5 plus x squared. Evaluated from 0 to 1, isn't it? Yeah, 0 to 1. And here it's gone and done that again. 0 to 1. All right. Oh man. All right. So when x is equal to 1, that first fraction is a 1/2. The next one's a minus 1/3. The next one's a minus 1/5. And the final one is, I'm going to have to expand this. Okay. Plus 1. Okay. And that's going to be 2 pi. Now, least common denominator, if I'm looking at it right, will be 30. Right? So that would be 15/30 minus 10/30 minus 6/30 plus 30/30. All right, 30 and 15 are 45, minus 10 would be 35, minus 6 will be 29. So double 29 is 58 pi over, oh, I didn't need to do that. let's leave it 29 pi over 15. I think that's right, because the 2 will go into 30 15 times, and then you add up what we had before. I think it was 29. So 29 pi 15ths. That's the answer they got. Oh man, I'm tired of sitting in one position. Any questions on that? Sorry that took a bit too long to do. That finishes, by the way, 7.3. Homework exercises here would be either 3 or 5. They're both at Calc Chat. And any of the odds 7 through 11, they're all at Calc Chat, with 7 being at Calc View. 13 or 15, both at Calc Chat. And any of the odds 17 to 21, with all those at Calc Chat, 17's at Calc View. Either 23 or 25, they're both at Calc Chat. 23's at Calc View. 27 is both at Calc Chat and Calc View. 29 or 31, they're both at Calc Chat. And this one may require a graphing utility. If it does, if you got one, use it. If not, you don't have to knock yourself out over it. 33 or 35, they both should be at Calc Chat. You can explore doing 37, it should be at Calc Chat, or 39. It should be at Calc Chat. Do 41, it should be at Calc Chat. And then either 43 or 45, they should both be at Calc Chat. And then do any of the odds 47 through 55, or at least through 53, they should be at Calc Chat. There's an exploration number 55, that should be at Calc Chat. And then there's a volume of a storage shed, that should be sort of interesting. That is at Calc Chat as well. Whoa, okay, sorry about that. I thought we were through. So back up a minute. Any of the odds 57 through 61, and they should be at Calc Chat. Then there's a project on Saturn, which is kind of a interesting example, so I'll let you figure out whether you want to follow up with that or not. You don't have to, for sure. All right, any questions on 7.3? All right, making pretty good headway today. Let's move on to 7.4, and I should have it up here. Well, let me I think it's here. That doesn't look like it to me. Okay, let me get out of that one. Discard. Let me close this one. I know we lost sharing. I'll be right back with it in a bit. Let me see if I can get this to move downward a little bit. Yeah, that's 7.3, so I can close that one out. And let's see if I can find 7.4. I opened it. Is that it? I don't think so. No. Okay. I can't see. They blackened out the thing, so I can't see my other one. So let me go down here. There's 7.4. Okay. And that's what I want to bring up. Let me. Okay. There's 7.4. Okay. I'm trying to get the new share. Okay, can you see, someone answer me, can you see my PowerPoint? Chapter 7, Application of Integration. Yes? Okay, good. It said it had closed it, but I could see it, and I couldn't see why they said it was closed. Okay, so what I'm going to do here is try to drag this thing out of the way. You can't see what I'm talking about, but it's a toolbar that is absolutely in the way. And we'll go this from current slide. If I can get this to do slideshow, we'll do from current slide. Okay, now 7.4, completely kinda new subject. Arc length, and then we'll do surfaces of revolution, not volumes of revolution. Okay, so the objectives here: first, find the arc length of a smooth curve. Secondly, find the area of the surface when you revolve that curve around an axis. That's what they mean by surface of revolution. Okay, let's start with arc length, first part of 7.4. Definite integrals are used to find arc lengths of curves and the areas of surfaces of revolution. We'll also do with arc lengths first. In either case, an arc, which is some segment of a curve, it could be a straight line, but usually a curved surface, okay? An arc, or a segment of a curve, is approximated by the straight line segments whose lengths are given by the familiar distance formula. The d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Basically an application of Pythagorean theorem. Okay? Now, they introduce a term here. A rectifiable curve is one that has a finite arc length. Okay? Now, I can't quite figure out why they call it a rectifiable curve, except that you can approximate it as a rectangle, I'm guessing. Okay? But that's not a good guess, I don't think. Okay. You'll see that a sufficient condition for a graph to have a function that's rectifiable between a f of a and b f of b is that f prime be continuous on that interval from a to b. Now what that means, you can't have any points, you can't have any cusps, you have to have a nice integrable function, a continuous first derivative on that curve. Because if you have a curve that does like this and then it coming like this is a very positive slope, that's a very negative slope. Hey, that first derivative is not going to be continuous. So such a function is called continuously differentiable on a to b, and its graph on the interval a to b is a smooth curve. No points, no cusps, no corners. They all have to be smooth transitions. Okay. Now, let's consider a function y is equal to f of x. Excuse me a moment. My throat's getting awfully dry. Consider a function y is equal to f of x that is continuously differentiable on some interval from a to b. You can approximate the graph of f by n little line segments whose endpoints are determined by the partition a is equal to x0, and then there's some other partition x1, x2, x3, x4, and the last one, x sub n, is at b. Okay, so in other words, you split that interval from a to b into n segments. Okay, they don't have to be uniform, but just n segments. So here's the picture here. x0 is the a one, then x of 1, x of 2, x of 3, x of 4, x of 5, till you get up to here, x sub n. Oh wait, I'm sorry, they're ending it right here. Okay, x sub n is right here. That's your b. So you're only going from a to b. Okay? Now, the arc length would be the actual length if you had, where is my pen here? My pen is not showing up now. Oh, there it is. Okay, I couldn't see it up there. The arc length would actually be the length of this curve. If you were riding on the car and watching your odometer, that would be how far you had gone. Okay? And because it's always curving, you already got the steering wheel turn, that's not anything straight about it. But let's say that you did a straight line from here to here. That's not a bad approximation of that. There's a straight line from there to there. It's a little worse, but it's not too bad. Then from here to here, here to there, wherever, until you get to the end. Those would be your partitions that would give you the straight line approximation in line segments. Okay? The actual curve is the length from here to there. What you do here is the distance between these 2 points, the distance between those two, the distance between those two, the distance between those two, wherever, and then say, how well does that approximate that? Fairly well, but not great. Okay? So, let's let the delta x of I be x of I minus x of I minus 1. In other words, between any two of those partitioning points there. The delta y would then be the distance on the y between the y values of those partitioning points. Then the approximate arc length would be the sum from I is equal to 1 to n, because you have n divisions there, of xi minus x of I minus 1 squared plus y sub I minus y sub 1 minus I sub y sub I minus 1 squared. I can't talk. Okay? So let's just pick one. Okay? When I is equal to 1, this would be x of 1 minus x sub 0 squared plus y sub 1 minus y sub 0 squared. Then you go to the next one, I equal to x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. So you see you're doing each of those lengths between every one of those points along that curve. Okay? And then you sum all those up, and here's the interesting thing. Here's the trick they use. This is pretty straightforward. Here, this is your delta x squared. That's your delta y squared. Now here's what they do. They divide everything inside here. This to me is, the way they've done it is weird, but divide everything inside here by delta x sub I squared. That would leave this being a 1 and this being dy delta y sub I squared over delta x sub I squared. So that delta y over delta x squared. But you can't just divide by this unless you also multiply by delta x, the square root of delta x squared, but that's just multiplying by delta x sub I. Okay? Well, what's this? 1 plus dy dx squared. The first derivative squared. That's inside the radical. Outside the radical, a delta x. So that approximation appears to become better and better and better as your norm gets closer and closer to 0. The norm being the length of the maximum partition along x. So as that delta x is approaching dx, incrementally small x, this gets better and better and better. In other words, your n is going to infinity. That gives you your arc length. So that then would be the arc length would be the limit as that norm is approaching 0, n is going to infinity, of this summation, which would be the square root of 1 plus dy dx squared times delta x. Now, remember that dy dx, we said it had to exist everywhere for every x in that interval, because it had to be smooth, had to exist. That's that requirement. So that it exists there. The mean value theorem guarantees the existence of some c sub I on that interval between x of I minus 1 and x of I, such that that c sub I will mirror the difference between that function. The first derivative there will mirror that. So the delta x of I, delta y sub I over delta x of I just becomes your dy dx, okay? First derivative of x at some value c sub I in that interval between delta x sub I minus 1 and x sub I, okay? They really bog it down with all sorts of verbiage. If you just think of that as being a dy dx, okay? Just think of that. That's y prime then, okay? You would jump right to it. So, because f prime is continuous on a to b, it follows that the square root of 1 plus f prime squared is also continuous. And if it's continuous, it's also integrable on that interval, which implies that then this s, which was the limit of that, all those summations, can be written as an integral from a to b, the first endpoint to the last endpoint, of 1 plus f prime squared, all under the radical square root of 1 plus f prime squared times dx, where s is called the arc length of that function f between a and b, because that's what you're integrating from. Okay? Whew. They said that in slide after slide after slide. Now they're going to give it as a definition. Let the function y is equal f of x represents a smooth curve on the interval from a to b. No points, no corners, no cusps, nothing like that. No discontinuities either, okay, by the way. Okay, so the function y is equal f of x represents a smooth curve on the interval a to b. The arc length of f between a and b is then the integral from a to b of the square root of 1 plus f prime squared dx. Similarly, for a smooth curve that you could say x is a function of y, g of y, going the other way, the arc length of g, that function g, as a function of y, between y is equal to c and y is equal to d, would then be, s would be the integral from c to d of 1 plus g prime of y, g prime squared, okay, g of y prime squared times dy, okay? Now, what does g prime of y squared mean? It's mean g dy, not g df dx, it's dg dy. So in other words, it's a dx dy most of the time, okay? You just flip them over. Now dy dx is dx dy, or whatever your function is. Okay, so let's do example 1. Okay, how are we doing on time? We've got a few minutes. I think we have enough. By the way, somebody was mentioned here, and this somebody was a guy named Christian Huygens. Okay, he's a Dutch mathematician who invented the pendulum clock, and James Gregory, a Scottish mathematician, both made early contributions to the problem of finding the length of a rectifiable curve. So there's 2 potential paper topics you could write on: who in the world is Christian Huygens, or who in the world is James Gregory, or how did either one of them proceed to try to come up with this, that type of thing. And there's also a little blurb there on page 275 for further information. There's an article there they give you. You could write on that one. You'd have to look it up and find it. So here's example 1. Oh, and this one's, I really don't like examples like this. They're so stinking straightforward, you tend to forget what you're doing, okay? that doesn't make a lot of sense, but let's do it. Find the arc length from x1, y1 to x2, y2. Just 2 points here, okay? On the graph of f of x is equal to mx plus b. So in other words, we're connecting those 2 points with a straight line, okay? Now, I better keep this in my lap. Okay. Now, it may be that I can write on this. It's going to be very fine in red. Are you okay with that, or would you rather me go to the whiteboard? Frankly, I don't think anyone cares. Okay, here's what we're doing. Find the arc length from that point x1, y1 to that point x2, y2 on the graph of f of x equal mx plus b. Okay, to do an arc length, one of the first things you've got to do is find out what f prime is, right? Because you got to square that. And what is f prime of mx plus b? Anybody? M. You take your exponent of the x, 1, multiply it by m times 1 is m, reduce the exponent by 1, that becomes a 0, okay? And x to the 0th is 1, so that's just m. The derivative of b is 0. So the derivative of f prime is m, okay? But what are we going to do with that? We're going to square it. F prime of x squared is then simply m squared, okay? Now, what do we do with that? We do 1 plus m squared. 1 plus f prime squared, and we take a derivative of it. I mean, not a derivative, square root of it. And then we do the integral of that square root dx, okay? And we're going from x1 to x2, because those are the limits on the x, from x1 to x2, from this point to that point, okay? Now, guess what? M's a constant. M squared is a constant. The square root of 1 plus m squared is a constant. So all that can come outside your integral. The square root of 1 plus m squared, that's a constant, times the integral from x1 to x2 dx. Well, that's just the square root of 1 plus m squared times the integral of 1 dx is just x evaluated from x of 1 to x of 2, okay? And that would be the square root of 1 plus m squared times x2 minus x1. Now, what is the m? Okay, right up here. Where is my, there it is. What is m? M is y2 minus y1. Oh, I'm pressing down on something, sorry. y2 minus y1 over x2 minus x1. Way back in algebra somewhere you had that. So let's put that in the formula we have down here. So that would be the square root of 1 plus y2 minus y1 squared over x2 minus x1 squared, all that's under the square root, times x2 minus x1. Yeah, quit that. Okay. Now I know what the beeping was. It's when I'm writing on the tablet and it presses into the keyboard. So let me scoot it down just a little bit so maybe it won't do it as badly. Okay, well, under that radical, if I can find it now, where is it? There it is. Okay, we could write that as x2 minus x1 squared plus y2 minus y1 squared over x2 minus x1 squared times x2 minus x1. Okay, well, this is a perfect square under a square root, so that would just be the square root of x2 minus x1 squared minus y2 minus y1 squared over x2 minus x1 multiplied by x2 minus x1. And these just cancel out. And what this is the length, okay, between those 2 points, okay. So the arc length is just the distance between those 2 points. Well, of course it is. It's a straight line. The arc length is a straight line. That is the length of the thing. And that's why I said I don't like problems like this. It has you going around in circles to get something that is intuitively obvious, okay? But they made you do it. So let's see if they do it any cleaner than I did. Now, what I don't know how to do is erase all this. I think that's why I hadn't been doing it. But it's written pretty lightly. Let's move on. Okay, your f prime, like we said, is equal to m, which is, like we said, y2 minus y1 over x2 minus x1. So it follows that the arc length is the integral from x1 to x2 of the square root of 1 plus y prime f prime squared times dx. That's your arc length formula. Well, that would be integral from x1 to x2 of square root of 1 plus y2 minus y1 squared over x2 minus x1 squared, which, just like we did, write the 1 here as x2 minus x1 squared over x2 minus x1 squared. And then you have this plus this over that. And your integral, you integrated this at the same time. They did 2 steps at once here. Okay, integrating this is all just a constant. I already took it outside, and that would just give you that constant times the value x. Evaluate that between x2 and x1. I don't like the way they did it, but it's correct. And that gives you that. Well, the denominator here under the square root, perfect square, the square root of a perfect square is just x2 minus x1. That's going to cancel that one out, and you're left with the length of the line between those 2 points. And that is your arc length of any straight line, is the distance between the 2 points. Okay. Which for the formula for the distance between 2 points in the plane, and that's exactly the arc length between those 2 points, is the distance between them, because it's a straight line. All right, that to me was almost a ridiculous example, but they did it anyway. Now, and I can't believe that's the only one they did in of all the exercises they had for arc length, examples for arc length, they did the one that made the least sense whatsoever. I mean, it was just intuitively obvious. They skipped example 2, they skipped example 3, they skipped example 4, they skipped example 5 before they went to area of surface of revolution. Okay? Now, we have 2 minutes left. I don't believe we'll be able to do example 2 in 2 minutes. So in exercise set 7.4, you can do example 5. Okay? It's at calcchat.com if you need it. hang on to the rest of them. Once we do some of the other examples, we'll come back and do those. So we'll start next time with example 2 on page 476. Are there any questions? I know that ran along. All I was doing was hearing myself talk because no one contributed anything. But do you have any questions? Anybody? Okay. Well, then I guess we'll pick up and go from there. Let's see. I'm cheating you out of 1 minute of your tuition dollars. I apologize for that, but I hope you'll forgive me. Let's move on, and we'll see you on Monday. So have a good... Oh, wait, we won't see you on Monday, will we? That's the bad news, isn't it? The good news is 4th of July is this Saturday. But the college, for some reason, chose to celebrate that on Monday. But of course, Monday and Wednesday classes have already lost 2 classes because we started the term on a Thursday, which didn't give us a Monday or Wednesday class. The next class day was a Monday, which was Memorial Day. So Tuesday, Thursday classes met on Thursday, then they met again on Tuesday. Monday, Wednesday classes didn't even start until a week after the Tuesday, Thursday classes did. And then they turn around and give us the 4th of July holiday on the 6th, which is a Monday, rather than giving it to us on the 2nd, which would have been a Thursday. At least we would have picked up one more day. No, they had us lose another day. So there's the bad news. We will not be meeting next Monday, but we will meet a week from today on Wednesday. So folks, keep chopping, okay? Have a good, safe 4th of July. Any questions? Any comments? Okay, that probably used my minute plus 1. Sorry about that. We'll see you in a week. Okay? And there is Joy Robinson. I didn't see Joy come in, I don't think. I don't know how you did that because I don't remember letting you in, but I'm glad you were here. Okay. Anybody else that I don't see? Okay, good deal. We'll see you in a week. Okay? Any last thoughts, parting shots? Bye-bye. Okay, I've got Nakaya here. Okay, or still connecting to audio, so Nakaya's here. And guess what? You're the only one here so far. While we're waiting, I'll go on and set up my slideshow. We don't have much left to do in this section. Okay. All right. Oh, here comes Roy. Okay. So we got doubled the class size just then as Roy came in. All right. While we're waiting for others to arrive, I'm going to try to do a little housekeeping here, moving some taskbars out of the way so they're less bothersome. And I'll get Nakaya and Roy out of the way here too a little bit in case that may be blocking. Okay, we'll go from current slide as well. Okay. Now, do either of you have any, wait. Sorry, folks. I'm going to have to pause a moment here. I forgot